In the previous lecture, we were discussing the directional coupler. We discussed about the physics and working principle of directional coupler. In this lecture, we will continue the discussion. We would also look into few more components that can be made using directional coupler and some other fiber optic components like polarization controller and fiber gratings. So, what we were discussing that if we have a directional coupler with two non-identical codes which have modes with propagation constants beta 1 and beta 2, then the fractional power that is in core 1 is given by 1 minus kappa square over gamma square sin square gamma z, and the fractional power in the core 2 is given by kappa square over gamma square sin square gamma z, where gamma square is equal to kappa square plus delta beta square by 4, and delta beta is nothing but the phase mismatch, which is the difference between the propagation constants beta 1 and beta 2. What we had seen that if delta beta over kappa is small, then we can have maximum coupling of power from one core to another core. This zeta max can be close to 1, and if delta beta is equal to 0, then we can have 100% coupling of power from core 1 to core 2. But if this phase mismatch delta beta is substantial, then we cannot have 100% transfer of power from core 1 to core 2 as shown here. So, for delta beta is over 2 kappa is equal to 2, the maximum power that can be coupled from core 1 to core 2 is 20%. Let us work out an example that if we take a typical value of kappa as 0.2 millimeter inverse, then we find that for delta beta greater than 4 millimeter inverse, zeta max would be less than 1%. This calculation is very simple, can be done very easily. How much is this delta beta? Let us work out some numbers and have a feel of delta beta, how much this delta beta is. We know that delta beta is equal to k naught delta n effective, where k naught is 2 pi over lambda naught. So, if I fix a wavelength, let us say 1300 nanometer, then delta beta is 2 pi over lambda naught times delta n effective, and for delta beta is equal to 4 millimeter inverse. If I calculate delta n effective from here, then it will come out to be 8 into 10 to the power minus 4, which means that if delta n effective is larger than 8 into 10 to the power minus 4, then the coupling of power from core 1 to core 2 would be less than 1%. How large this is? How large this delta n effective is? You can compare it with core cladding index difference in single mode fiber, which is 3 into 10 to the power minus 3. So, if you have a single mode fiber, if I draw the refractive index profile R, and this is NR, this is N1, this is N2. So, this difference is typically 3 into 10 to the power minus 3, and here delta n effective, which is the difference between the propagation constants of two modes of two different waveguides or two different fibers, delta n effective is typically 8 into 10 to the power minus 4. If it is greater than 8 into 10 to the power minus 4, then there would be coupling of power which is less than 1%. So, if you compare it, let us say there is another fiber like this RNR. So, these are two non-identical fibers. So, this is delta n effective 2, sorry, this is n effective 2 and this is n effective 1. So, if you compare these two, the difference should be much smaller. And if you calculate the value for maximum coupling of power for example, say for more than 99% coupling of power, then this delta N effective should be less than 8 into 10 to the power minus 5. Now, we can use this directional coupler for multiplexers and demultiplexers also. Here we utilize the fact that the coupling coefficients kappa are wavelength dependent. So, if we send two wavelengths lambda 1 and lambda 2 through this device, then what will happen? Okay. Let us say at lambda 1 the coupling coefficient is kappa 1 and at wavelength lambda 2 the coupling coefficient is kappa 2. We know that for phase meshed case, let us consider phase meshed case for convenience. P1 is equal to Pi cosine square kappa L, this is the power in core 1, and P2 is Pi sine square kappa L, power in core 2. Now, if I choose this length L such that kappa 1 times L is equal to m pi and kappa 2 times L is equal to m plus half pi. Remember that kappa 1 is the coupling coefficient at lambda 1, kappa 2 is the coupling coefficient at lambda 2. In such a case, at lambda 1, at wavelength lambda 1, P1L would be equal to Pi because kappa L is equal to m pi, and P2L would be 0 because kappa 2 L kappa 1 L is equal to m pi, so P2 would be 0. So this would be P1 and this would be Pi and this would be 0 at lambda 1. At lambda 2, since kappa 2 L is equal to m plus half pi, so this will give you P2 is equal to Pi and this one will give you P1 is equal to 0 at length Z is equal to L, which means that lambda 1 will come out from this core and lambda 2 will come out of this core. Okay. If I plot normalized power, that is P1 over Pi or P2 over Pi as a function of Z, then how it varies? P1 over Pi would vary like this and P2 over Pi would vary like this. So, what I find that at this value of Z, I have power in core 1 at lambda 1 is equal to Pi and power in core 2 at lambda 2 is equal to Pi. So, lambda 1 will come out from this port and lambda 2 will come out from this port. So, this is how I can choose the coupling length, demultiplexing length for such a coupler. So, what I am able to do with the help of this? I am able to separate out two wavelengths into two different fibers. So, this works as wavelength demultiplexer. In the same device, if I now launch lambda 1 from here and lambda 2 from here, then for a given length L, which we can find from the previous slide itself, for that length L itself, both the wavelengths will come out from a single fiber. So, I can multiplex two wavelengths together. So, these kind of couplers are known as WDM coupler because they are used in WDM systems. Let us now look at some practical parameters of a directional coupler. A directional coupler is a 4-port device and we can name the ports like this. This is the input port, this is throughput port, this is cross port or coupled port, and this is reflection port. An important parameter is coupling ratio. Coupling ratio in percent can be defined as power in the cross port divided by the power in cross port plus throughput port. So, power in cross port divided by total output power times 100, this is in percent. So, this is coupling ratio in percent. In dB I can define it as 10 log PC plus PT over PC. Then I can also define the excess loss as 10 log Pi over PC plus PT, which basically tells you that how much loss this device will introduce, okay, what is the inherent loss in this, because not all the power is coming out, whatever power you are inputting. So, not all the power is coming out. Then we have insertion loss. Insertion loss is for a coupler or switch. So, it is defined as 10 log Pi over PC, which is nothing but summation of coupling ratio plus excess loss. Then another important parameter of a directional coupler is the directivity, okay, which is defined as 10 log PR over Pi. That is how it is the measure of how much power comes back. Okay. We want that all the power should go in one direction, in the forward direction. So, this defines how much power comes back. Okay. So, larger the power comes back, poor is the directivity of the coupler. So, for a good directional coupler I should have low insertion loss and high directivity. For a typical 3 dB commercial coupler, excess loss is less than or equal to 0.1 dB, insertion loss is about 3.4 dB or less, and directivity is better than minus 55 dB. So, now I can go into some other fiber optic component. So, apart from this directional coupler, another important component is polarization controller. We sometimes need to control the polarization state in the fiber, and for that we require this polarization controller. This polarization controller is based on banding effect in the fiber. So, we will discuss that, how banding of a fiber can control the polarization state of the light which goes through the fiber. If I have a circular straight single mode fiber, since it is single mode fiber, so and I am always working in weakly guiding approximation. So, the modes are LP modes. So, in a single mode fiber I have LP01 mode, and this mode has two orthogonal polarizations, and these two orthogonally polarized modes have same effective index, okay, because it is a weakly guiding fiber. But if I band this fiber, then banding introduces stresses in the fiber, and this makes the fiber linearly birefringent, which means that now this polarization will travel with different velocity and this polarization will travel with different velocity. That is, this polarization will see different refractive index of the fiber as compared to this polarization. Okay. And what happens is that the fast axis in the plane of the loop and slow axis in the plane perpendicular to the loop. So, if I have a fiber which goes like this, if I make a loop like this in the fiber, and this is z direction and this is x direction, then this axis is the fast axis which is in the plane of the loop, and this axis is slow axis which is perpendicular to the loop. Okay. So, here it is. So, if I have this kind of situation, so the loop is in xz plane. So, your x axis is the fast axis and y axis is the slow axis. So, there is birefringence introduced in the fiber, and the difference between the effective indices of y polarized and x polarized mode would now be given by delta n effective is equal to n E y minus n E x, and this is dependent on this birefringence depends upon what is the overall diameter of the fiber, what is the cladding diameter, what is the thickness of the fiber, and what is the bending radius. Okay. So, it is given by C times B square over R square, where B is the outer radius of the fiber and R is the radius of the loop. And it is intuitive because this birefringence is produced by stresses induced in the fiber by bending. So, if the fiber is thicker, so if you bend a thicker fiber, then the stresses introduced would be more. A thin fiber would be very flexible. So stresses introduced would not be very large. So, the birefringence would be smaller in thinner fiber as compared to in thicker fiber. Then radius of the loop, if the radius of the loop is large, so bending is very soft, it is not very strong bending, then birefringence would be smaller, and if you give it a very tight bend, that is radius of curvature is very small, then birefringence introduced would be large. Typically for silica glass fiber, this C, which is the constant which depends upon the material of the fiber and elasto-optic properties of the fiber material. So, for silica glass fiber, this is given by C is equal to 0.133, typical value is 0.133 for silica glass fiber at wavelength 633 nanometer. Now, since there is a birefringence introduced in the fiber, so this polarization is traveling with different velocity as compared to this polarization. Now, if at the input end of the fiber you excite both the modes simultaneously, both the polarization simultaneously, then as they will propagate in the fiber, a phase shift would be accumulated between them. Okay. As they propagate in the fiber, a phase shift would be accumulated between them, and the state of polarization at any value of Z inside the fiber can now be found out by superposing these two polarizations with the accumulated phase shift. Okay. So, you can find out the state of polarization at any distance Z, and so since there is a phase shift accumulated, so this polarization state will slowly rotate. Okay. So, let us say after one loop, if I have one loop of radius r here, capital R, and number of loops, let us say n is equal to 1, n is the number of loops, then how much length does it travel when it goes through this loop? So, the length would be 2 pi r times n, and if n is equal to 1, then it is 2 pi r. So, so this is 2 pi r for n is equal to 1, and for n number of loops this distance would be 2 pi r n. So, what would be the phase shift accumulated if there are n number of loops? So, phase shift would be 2 pi over lambda naught times delta n effective times the length, total length in the loops, which is 2 pi r n. If I now put the expression for delta n effective from here, then it would be 4 pi square over lambda naught times C times B square over R times n. Okay. Now, since delta phi is equal to this, so I can now have a particular radius or or the number of loops to introduce a particular value of phase shift. Let us say I take n is equal to 1 and then I calculate what would be the radius of the loop to introduce a phase shift of pi, or what is the radius of the loop to introduce a phase shift of pi by 2. And I know that a phase shift of pi by 2 corresponds to a quarter wave plate. If I talk about bulk optics, in bulk optics if I have birefringent crystals, then out of these crystals I can make quarter wave plate, half wave plate. Quarter wave plate means a path difference of lambda by 4 or phase shift of pi by 2. So, I can immediately find out the radius corresponding to quarter wave plate if I put delta phi is equal to pi here and find out correspondingly the radius. So, this radius comes out to be 8 pi over lambda naught times c times b square times n for n number of loops. For half wave plate, I am sorry, there is a typographical error here. For half wave plate, this quarter should not be there. Delta phi is equal to pi and the corresponding radius is given by r HWP is equal to 4 pi over lambda naught times c times b square times n. What are typical values of these radii? If I consider a silica glass fiber with B is equal to 62.5 micrometer, which is the standard cladding radius, and I give it a band of about 3 centimeter radius, and I consider, let us say, C approximately equal to 0.133 at lambda naught is equal to 633 nanometer. Then for n is equal to 1, if I consider n is equal to 1, then the radius of quarter wave plate would be about 2 centimeter. Okay. Radius of the loop corresponding to quarter wave plate is about 2 centimeter, and the radius of the loop corresponding to half wave plate is about 1 centimeter. Okay. So, this much a loop of this band radius will introduce a phase shift of pi by 2 or path difference of lambda by 4, and a loop of this band radius will introduce a phase shift of pi or path difference of lambda by 2. So, with the help of this, with the combination of these loops, I can virtually obtain any polarization state. Okay. How? Well, I take a fiber and make loops like this. Okay. Let us say the radius of the loops are such that, or radii of the loops are such that this loop introduces a path difference of lambda by 4. So, this is the quarter wave plate, this is equivalent to half wave plate, and this is again quarter wave plate. Now, let me fix these points A, B, C and D. So, these points are fixed, and now these loops can be rotated. So, if you have this fiber and there is a loop here, then this loop can be rotated like this. This loop can be rotated. This loop can also be rotated. This loop can also be rotated. Okay. What do I achieve by rotating these loops? You see that if this is the loop, okay, then I have certain principal axis. This is the fast axis, this is the slow axis. When I change the rotation, if I rotate it, if I change the orientation of this loop, the fast axis is this and slow axis is this. So, basically what I am doing, I am changing the principal axis of the loop. Okay. It means that it is equivalent to rotation of your half wave plates or quarter wave plate in bulk optics. So, by rotating these loops I am virtually creating different orientations of half wave plates and quarter wave plate. And so, the phase shift introduced now would be different. I can control the phase shift that can be introduced. So, with the combination of these and different rotations, I can convert any input polarization state into any other polarization state. So, this comes out to be very efficient device in terms of polarization controller. Okay. The only thing is that since we are giving tight bands here and bending always introduces loss. So, this kind of device would introduce certain losses in the system. Okay. So, this is how I can rotate, for example, this and obtain any polarization state. So, in this lecture we had seen how directional couplers can be used as multiplexers and demultiplexers. We had also seen in this section how we can make power splitters, how we can make switches using directional coupler. We had also seen that with the help of introducing certain loops in the fiber, we can make polarization controllers. These polarization controllers are commercially available also. In the next few lectures, we will study some other components based on optical fiber, and these components involve gratings in the core of the fiber. What you can do, you can in the core of the fiber you can introduce periodic refractive index modulation, and this periodic refractive index modulation can alter the spectrum of the light which you pass through this fiber. So, with the help of this we can make several components, we can have applications of these components in different devices, in telecom devices as well as in sensing devices. So, we will study these fiber gratings in the next lecture. Thank you.